now, guys, you now know how to do type 1, type 2, binary, and polyatomic naming and writing formulas. You should. You have an idea how to do it. We will keep practicing these and keep practicing these until we finally get them right. Okay? But now we're going to move on to type 3. Type 3 is a little different. So type 3 is probably the easiest you will do. So you will love type 3 nomenclature.
Yeah.
Okay? So these are the ones with covalent bonds. So we'll start off with this quick little video. Please pay attention. There's a lot of information I may not be saying or giving notes, but you need to listen to this. You'll be responsible.
Covalent bonds. In this video, you are going to learn about covalent bonds, how they are made, and how they form. If you haven't seen it already, first have a look at our video, Structure and Bonding. Only the noble gases exist naturally as single atoms. All the other elements of the periodic table have partially filled valence shells, or outer electron shells. Atoms bond by swapping or sharing electrons in their outer shells. When very different atoms react, like metals and nonmetals, they normally swap electrons. This is ionic bonding. But when similar atoms react, like nonmetals combining with other nonmetals, they share electrons. This is covalent bonding. Nonmetals are found on the right-hand side and upper part of the periodic table. Some common nonmetals are carbon, nitrogen, oxygen, and the halides. They have shells of electrons that are normally half or more than half full of electrons. Since they have a strong attraction for a few additional electrons, it is energetically unfavorable for them to lose electrons, so they share electrons by overlapping orbitals. This makes a bonding orbital, or covalent bond, that contains 2 electrons. If there is space in the outer shell, a non-metal atom can form double or triple bonds, like in oxygen or nitrogen. In the displayed formula of a compound, we represent a covalent bond with a straight line, like this. We can also represent a covalent bond as a dot and cross diagram. These diagrams show only the valence electrons. To learn more about dot and cross diagrams, watch our video on dot and cross diagrams. Covalent bonds are directional, which means they are in a fixed position, like holding hands. This is different from ionic bonds, which are formed with an electrostatic attraction between charged ions. The overlap between orbitals means that the atoms in covalent bonds are very close. These things make covalent bonds strong. There are 2 kinds of covalent structure: small molecules, like water, and giant compounds, like diamond. Because the electrons in the bonds are evenly shared, bonds are not polarized. There is little attraction between molecules, and forces between molecules are weak. Compounds made from small covalent molecules have low melting and boiling points, and are volatile. They also don't conduct electricity. Carbon and silicon tend to form giant covalent compounds. These bond in the same way, but instead of forming small molecules with 1 or 2 bonds, they form 4, making up huge lattices or chains of many, many linked-up atoms, the basis of the organic chemistry of carbon or the chemistry of rocks. One common example is diamond, which is made of carbon. Each carbon atom forms 4 covalent bonds because it has 4 electrons in its outer shell to share and has space for 4 more. If every carbon atom forms 4 bonds with 4 other carbon atoms, and each of these forms 4 bonds with 4 other carbon atoms, and each of these forms 4 bonds, we very quickly end up with a very large structure. These compounds have very high melting and boiling points because you have to break covalent bonds rather than intermolecular forces to make them free enough to act as liquids or gases. The covalent bonds hold them rigidly in place in the giant lattice. Allotropes of nonmetals bond covalently. Allotropes are different structures of the same element. You can learn more about these in our video, Allotropes of Nonmetals. So to finish, here's a challenge for you. Which of these compounds are covalent? Pause the video for a moment whilst you think.
Whilst.
Have you considered their physical properties and where the elements come from on the periodic table? Solved it? Okay. The answer is all of these compounds are covalent. Carbon dioxide, carbon monoxide, and methanol are all small molecules. Organic molecules form covalent bonds between hydrogen and carbon. C70 is a fullerene, a carbon molecule shaped like a rugby ball, closely related to the Buckminster fullerene. Silicon dioxide is a giant covalent structure and just like diamond, but has oxygen atoms bridging between 4 coordinate silicon atoms. Hopefully, you now feel confident identifying covalent compounds and recognizing their properties.
Okay, so covalent bonds do what with their electrons?
Share them.
Emma? What do they do with them? What do the electrons do in covalent bonds? Yeah, but you need to pay attention, okay? I ask you to watch the video. I expect you to watch it, okay? Okay, so they get shared. Thank you, Mason, for saying that.
You're welcome.
Okay?
I paid attention.
And it shows. Thank you. Okay, so covalent compounds are between a nonmetal and a nonmetal. This is where on that flow chart it says, is the first element a metal? And you say no. And you say no, it's going to take you to the covalent compounds. They are two nonmetals. Where an ionic is a metal and a nonmetal, these are just two nonmetals. So it's going to be, everything's going to be between this little group of elements right here. Okay? So far, so good? Covalent compounds. The valence electrons are shared. They are shared. Most of the covalent compounds are neutral. Just like ionic compounds, they will cancel each other out and they'll be neutral compounds. And they form in something called molecules. Ionic compounds are called formula units. Covalent compounds are called molecules. But as you know, some of these groups, some of these molecules, these groups of covalently bonded atoms will have a charge on them. Your polyatomic ions. Remember those from earlier today? What is nitrate's formula? What is nitrate's formula? Think you will?
NO3.
Good job. NO3 minus 1. That's nitrate. It's on the back of your periodic tables, right? Some of your covalent compounds are going to be polyatomic ions. They will act like anions in a compound, this big group. But most covalent compounds are neutral. Most of them are neutral. Okay? They form in a group called molecules. And a molecule is a neutral group of atoms joined together by covalent bonds. They are held together by these covalent bonds which are sharing electrons. And when they share electrons, they're a little tougher to come apart. So they form a molecule. They form a molecule. And here are 3 atoms, hydrogen, carbon, and oxygen. With these 3 atoms, I can form any of these. I can form water, I can form carbon dioxide, and I can form ethanol. And I can form lots and lots and lots of other things. Just like in the video, it said they combine together. Those 4 carbons can then join with 4 more carbons, and then 4 more carbons, and 4 more carbons. Covalent compounds can be, these molecules can be huge. Huge enough for your DNA. Your DNA is held together by covalent bonds. Also, antibodies. The antibodies in your body are covalently bonded. They are big, bulky molecules. Some are long, stringy things like your polymers, but molecules can be huge or they can be very small. Ionic compounds can't be that way. Ionic compounds just share an attraction. Okay, that attraction, if it gets too many, this falls apart. Covalents share, so they tend to build big molecules. Molecular compounds are composed of molecules. Type 3 are molecular compounds. And the thing about these is they don't break apart in water like ionic compounds do. They are not easily led astray by water. They'll dissolve in water if they can. But they're not going to break apart. The molecule will still stay together. Sugar is a covalently bonded compound. And we know sugar's still in water when you dissolve it in there. Okay? It doesn't break apart into carbon and hydrogen and oxygen. I don't drink sugar water and go, it's a little too carbony for me today. That doesn't happen. The sugar molecule stays in place. Okay? So far, so good. Yes. Here are some properties. Comparison between ionic and covalent compounds. Ionic compounds will always exist as a solid at room temperature. You will never find them in a liquid or gaseous form. It just doesn't happen. But covalent compounds can exist as a solid, a liquid, or a gas. As a solid, it could be a sugar molecule. Sugar molecule. It could be as a liquid, it could be water, H2O. As a gas, it could be NO2, solid, liquid, and gas. Covalent compounds can take on any of these states of the matter. Ionic compounds cannot. Ionic compounds have high melting and boiling points. You try to melt salt, it's not going to happen. What if you try to heat up sugar? Sugar melt easily? Yeah, oh my gosh, yeah, sugar melts so easily. In fact, when I make my icing for my cookies, I take 4 cups of sugar. 4 cups of sugar. And I dissolve it with 6 tablespoons of water. And it becomes a liquid. Crazy. Crazy how much it can dissolve. Okay? So sugar is very soluble in water, and it has a very low melting point and boiling point. I just said dissolve. I meant melt. Also, when you make rock candy, I'm fascinated by the fact that I can dissolve that much sugar in water. But when I make rock candy, you basically heat up sugar and it melts. Then you put a little water in that too. But sugar melts so easily, so easily. Conducts electricity. Ionic compounds will conduct electricity when they're dissolved in water or molten. Covalents won't do that. Covalents don't come apart in water. Okay. Excuse me? And they transfer, ionic compounds will transfer valence electrons where covalents share them. A little bit tougher of a bond. Like playing Red Rover. You guys ever played Red Rover as kids? When you say Red Rover, I dare someone over and you got to run and break through them. Well, if you're just standing side by side, they're going to be able to break through you? Yeah. They're going to go right between us. But if we're holding hands like this, we may be able to stop you a little more. Okay? So, ionic is they're standing side by side, covalent they're holding hands. Does that make sense? Yes? Covalent compounds, we'll talk more about those as we get into bonding and stuff. That's just kind of a nice, quick way of introducing you to covalent compounds. Now, I'm going to show you these two videos maybe a little bit later or tomorrow, depending on our time. But naming covalent compounds. These are your type 3 compounds. They're called molecular compounds. And when you name them, you have to use prefixes. Now, these are on the back of your periodic table in the lower right-hand corner. There's a little box of prefixes that says, do not use these with metals. You see that? No, look. You never use prefixes when you're naming something with a metal in it. Only your two nonmetals. Okay? So let's write a formula first. If I've got dihydrogen monoxide, what does di mean?
2.
What's hydrogen symbol? H. So hydrogen symbol is H. It means I have two H's. Dihydrogen, just like a bicycle means two wheels.
And you've got 1 O.
Now I've got 1 O. Mono means one. O is oxygen. That's it. You don't have to look at charges. You don't have to look to see if it's type 1, type 2. Only thing you have to do is turn it over and look at your prefixes. That's all you have to do. These guys are simple. Very simple to name and write formulas for. Make sense?
You have to put the 1 or
No, you don't. I just got rid of it to show you. What would the formula be for carbon tetrafluoride? What do you think? Don't shout it out. We'll everyone take a minute to see if you can figure it out. And you do give me a thumbs up that you got it. Okay. What is it going to be? CF4. Good. CF4. Carbon. Now here's the thing. We never use mono for the first element. So it's just the first element's name. Why? I don't know. No one asked me. No one asked my opinion on it. I would have said monocarbon. But for some reason the rule is you never use mono with the first element. Okay? And just like you name your binaries, first element keeps its actual name, second element turns into IDE. Because these are binaries. They're all binaries. Okay? Now let's name this guy. How many nitrogens do I have?
2.
So it's going to be what? Di-nitrogen. And then what? What's 7?
Heptogen.
Hepta oxide. Dinitrogen heptaoxide. These things sound really, really weird, but they're correct. Okay? Now some people just say heptoxide, some people say heptaoxide. I've heard it both ways. I think it all depends on what textbook you used. So either are fine. Okay? When you do these online, I will have both in there for you, so it won't count you wrong. Does it make sense? Okay, but here's the thing. Never, ever, 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 never use these with metals. If you see any of those elements on the left-hand side of the periodic table first, Do not use prefixes. Do not say it is trialuminum dioxide or something like that, or Al2O3, dialuminum trioxide, or what, NaCl, sodium monochloride. Do not say that. You never use prefixes when a metal is present. Okay? These are only for type 3, non-metal with non-metals. Does that make sense? Are we all good with that? Yes? Okay, and I think that's good acids. We're not going to do acids just yet.